So, all right. So e to the negative 3t is periodic? No, at least Mikael doesn't think it is. And he's right. It's not periodic, right? What's it mean to be periodic? It repeats. E to the negative 3t is never going to repeat. I'd call that a monotonic function. It just goes like that. Has each value one time. Right? Would that have a Fourier series? No. Why not? What does a function have to be to have a Fourier series? It has to be periodic. Yeah, I like that. Yeah, it has to do this, right? But no, this guy is not periodic. He does have a Fourier transform. All right. I'm not going to get into Fourier transforms with non-periodic signals. There is a formula for it. They'll talk about that in 3111, right? In signals and systems. I'm not going to get into that so much here. I'm going to focus on it as it relates to really do a periodic waveform. All right. So we talked the other day. I mean, what I see if I look at something like that audio signal here, I can put it through what I call a spectrum analyzer, a device that will compute the Fourier transform. It's basically just a computer device. All I have to have is an ABC that can give me digital samples, and I can take those digital samples, put them through a Fourier transform algorithm, and I can get these coefficients and plot what this thing looks like. Now, fundamentally, looking at that picture, it's important to probably understand what that picture is telling me. What is that picture telling me? Yeah, this is a picture in the frequency domain, and what is it telling me? So my app didn't label the axes here, but what this is labeled frequency in F in hertz. Okay. What are these guys here? Yeah, it's the frequency buildups. I guess that's a way to refer to it. I guess the way I kind of referred to it the other day is I said it's the frequencies where the input signal has information. Right? In other words, where there is some content. Like, so for instance, if this is my input here, x of t, then what I'm showing here is the absolute value of x of omega. Somehow I'm trying to show what frequencies, in other words, so at what values of omega do I have information? That's what this thing was telling me. All right, that's the basic concept. And if I have a non-periodic waveform, it'll tell me some stuff. All right. And if I have a periodic waveform, it's going to look like this, where these guys kind of sort of look like impulses shifted to, I don't know, this, I'll choose this guy right here. Looks like he's right around 412, right? Based on the sort of arbitrary, weird way that my app labeled the axes. I'll say that there's an impulse that looks like it's at 2 pi times 412, like that. Kind of an impulse, right? Well, how is that kind of an impulse and not really an impulse? What's the difference between this guy and an impulse? An impulse is infinitesimally thin, right? This guy's a little chubby, he's a little bottom head, right? Whereas opposed to a real impulse is paper thin, right? So this guy's not, right? Now there's a reason why he's not, but in reality, what he looks like is he's an impulse that's been kind of spread out a little bit. All right, and there's some reasons behind why that is, which we won't really get into. If you're interested, you can ask me about that. But what you're always seeing in reality is that when you take the Fourier transform, it kind of approximates that, right? It doesn't really hit it. All right. So again, the way to kind of think about this is we live in the time domain, right? Stuff happens in time. All right. I can think of my life having an x-axis that was t, and I'm just watching what happens. So if I had some audio signal that I measured, it would look like this. Let's say, so this audio signal apparently has a couple of different frequencies in it, meaning a couple of different sine waves added together. So an audio signal is a good example, right? This could be, I don't know, this could be the bass and this could be the snare, right? I can be adding sort of what's coming together from two different drums, right? Let's say that I put together, and I'd have some audio signal that looks like this. And when I look at it in the frequency domain, I get these sort of impulses that are basically located at the frequencies where there's those notes. Okay, that's the basic idea. All right. So the other day we kind of went through this for a pure cosine, all right? And basically said, I'm going to jump to here, right? So from what we said the other day, I basically have this guy here. So if I have a periodic waveform x of t, which we've got three different ways of writing this, I'm kind of sticking to this version of it, where it's in the complex form of the series. But I could also say this guy was C naught over 2 plus, all right, so if I have that version of the series, where does the summation start? So if I have C values, where does that summation start? N equal 1 and goes to infinity. And I'd write that as what? What goes under the summation? Not alpha. So this is my complex form of the series. That's where I use the alpha coefficients. Go for it. You're on the spot now. No, you're on the spot. You get there's no getting out of it now. So, yeah, so this is where I put C sub n, cosine of n omega naught t. And what do I do? If it's just the cosine form of the series, there's a phi sub n. And the phi, basically what we're saying is for every harmonic, I have different amplitudes and different angles. And somehow there is just the right amount and just the right phase shift that I need to be able to look like the original input signal. Okay. So a Fourier transform is related to this thing. What I do is I take the alpha values and I say that there is a set of impulses that are weighted by the alpha values at the frequencies where I have information. And the frequencies where I have information are going to be what? They're going to be at omega equals 0, at omega naught. What would be the next one? What's that? Not well, so at a frequency, so omega naught's my fundamental. That's our definition of the fundamental, right? So I have information at 0, omega naught. If it's a periodic signal, what would be the next frequency? What is omega naught? What's our definition of omega naught? Fundamental frequency, right? So fundamental frequency is what we call, what number harmonic is it? Somebody other than Jeff. First. Okay. All right. So if it's the first harmonic, what's the next one I'm going to have? Well, so the next one I'm going to have is the second harmonic in general. So a lot of the examples you've had probably don't have a second harmonic, but there is the next one is the second. All right. The next one after that would be a third. So those frequencies would be at 2 omega naught, 3 omega naught, 4 omega naught, 5 omega naught. Basically, what are they? They're integer multiples. They're harmonically related. They're integer multiples. Okay. So in the frequency domain, what I'm going to do is I'm going to have impulses that are located at those frequencies. Okay. And to get the Fourier transform, I got a couple of steps, right? The first step is I got to get the Fourier series coefficients. Then I got to map those to the right frequencies. And then I got to figure out what this x of omega actually is. Now, we said it last time, and I doubt you've really thought about it much since, but basically this guy is a complex function of a real variable. The hell do I mean when I say it's a complex function of a real variable? What the heck am I saying when I say that? I have something that's a complex function of a real variable. What do I mean by that?
A value in there somewhere.
Just J value in there somewhere, yeah. Yeah, so basically it means that X is complex and omega is real. So I plug a real number into this function and I get a complex number out. All right, so when I talk about that, a complex function of a real variable, just to be clear on that, I guess what I would say is I have some function. The way I think of a function is I plug a number into it. right? So this guy is x of omega. I plug omega in, and I get x of omega out. So I put a real number in, and I get a complex number out. All right, you have that right now with Yahoo. You guys told me the other day you're doing transfer functions, so you got h's of omega, and that came from impedance or something like that. So you had j omega c times r over 1 plus j omega c times r, something like that, right? You get some kind of transfer function like that. And what is that? This is a complex number. Omega is a real number, okay? So what's that mean? So I put a real number in. That if I actually want to visualize this guy, what do? I got to make two graphs, right? So I make two graphs, both versus omega. And what are the two graphs I draw? If I have something that is x of omega, so if I gave you this, Yahoo's giving you that, something like that, or you get that from a circuit, right? How do I draw a graph of that? Use what? Cry a lot? Cry a lot? So if I gave you a complex set of complex numbers, how would you graph that? Yeah, I could graph the real on one graph. I could graph the complex on the other part, or the real and the imaginary. Or I could say, what we talked about the other day is I could plot the magnitude and I could plot the angle, right? So I could plot those two things. And usually that's, you could do the real and imaginary part, but often we use the real, or sorry, the magnitude and the angle. Because if you think about it, these things here, when you talk about a circuit, the magnitude and the angle relate to the phase shift and the scaling that the circuit's going to apply, right? The real part and the imaginary part don't really mean a whole lot to me usually. All right, so we talked about that the other day. All right, now what I want to do is, and here, this was the idea we talked about the other day, complex functions of a real variable. So we said I got to make one graph for the magnitude, one for the angle. All right, want to know more about that? Section 4.6 talks about that kind of as a general thing. Now, if I did this the other day, I did it for a function that had only a single impulse that did an example, but that could totally be like in Yahoo. Again, Yahoo might give you something that's, I don't know, I'll put numbers in it. 3j omega over 1 plus 3j omega. Right? That's a complex number, right? You would plot a magnitude and an angle for that, and they would be smooth functions. They wouldn't be these impulsive discontinuous things. All right. You'll learn plenty about that. All right. Yahoo probably doesn't call it a complex function of a real variable. It doesn't need to. This is more of a math class. I kind of need to. All right. I know that sounds scarier, but if I just let you plot it, it's probably easier to plot it, but that's what it is. All right, so the other day we talked through this example, right, where I had a single cosine, and we determined what the magnitude of x looks like, what the angle of x looks like. So what we're going to do today is we're looking at a more complicated example, right? And you have something like this. This is problem 3 on homework 8, all right, where I've got this guy. So x of t is that. And I want to figure out what its Fourier transform is, and I want to plot it. Okay. And I'm going to approach this the same way we approach this stuff in the homework here. So, all right. This is a periodic waveform, right? What's the fundamental frequency here? I could use that GCD approach if I wanted to, but I can kind of do this one by inspection. 60 hertz. All right, 60 hertz. So omega naught would be 2 pi 60 rads per second. Like so. Okay. All right. What frequencies do I have here? So, or what harmonic numbers? And let's do it this way. So if I have the A, B, C form of the series, right? So there's, I guess, let me do it this way. The A/B form or the C form, right? The AB form is where I got a sine and cosine together. C is what I call the shifted cosine, and then I have the alpha version. Okay. What values of n in this form of the series, what values of n do I have here? 0. Okay, which 0 is what frequency? Okay, which is what's the value of the frequency for that? 0. All right. So in other words, a DC signal doesn't vary. So I got an n equals 0. I have an n equal 1. Which one is the n equal 1 term? So this is our n equals 0. What's this one? N equal 1. What's this guy? N equal 3. All right. So those are so these, I should say, these are, just to be clear about this, these are the non-zero harmonics. Right? Doesn't mean that there isn't necessarily an n equal 2. It's just that's z equal to 0 in this particular case. Right? If I talk about the alpha form of the series, what are the n values that I have there? I definitely have a 0. What else do I have? Yeah, I get a plus minus 1 and a plus minus 3. Why do I have a plus minus where I didn't in the other form? Is it in the complex form of the series? It's basically two rotating vectors, two vectors that rotate over time that create a cosine. Right? So one rotates in the positive direction, one rotates in the negative direction. So I always need to have a positive and a negative together, right, to cancel out to form what I have on the left side here. Okay. So all right, those are the values that I have. So now what I want to do is I want to go through this process. Right. So I got, my process was, all right, I want to figure out the Fourier series coefficients alpha n. Okay. I want to map those alpha n to the right frequencies. And then I want to figure out this x of omega as the sum of the impulses located at the right frequency. Right. And the sum that we're making here is x of omega is the sum from n equal negative infinity to infinity alpha n delta of omega minus n omega naught. Right? That's what we're going to figure out. So let's, and this is going to be helpful to us to figure out how to relate between those things. All right, so here we go. Step 1. You guys determined for me already that this guy here was an n equals 0. This guy was n equal 1. This guy was n equal 3. Okay. Now let's identify this here. So I already know that I want to get to the alpha form of the series, the complex form of the series. So somehow this guy is equal to n is equal to a0 over 2 plus this ugly thing, an cosine n omega naught t plus bn sine n omega naught t plus is equal to this ugly guy. All right. So those there's a set of coefficients for each of those things that makes all of them equal to each other. Okay. So we need to determine the coefficients alpha n specifically. All right. Those are the ones I want to get. So help me out. So we have n equals 0. We know what, for n equals 0, looking at this thing, what is my alpha n right here? So if I plugged in n equals 0 into this formula, right, this one here, I would get alpha n times e to the 0. Right. So in other words, what I would get is alpha 0 is equal to what number? Alpha 0 is equal to 5. alpha 0 is equal to 5. All right, one of these days I'm just going to stop using the formula from the book. A0 over, so that is also equal to the DC term. A0 over 2 and C0 over 2. So A0 is equal to C0 is equal to 10. All right. The DC term in that guy is 5. All right. We got to do, let's do the harder ones. Which form of the series do I have for n equal, for the n equal 1 term? What form of the series do I have? I have the shifted cosine. I don't even bother, for me, I don't bother going back to the formula sheet. What I say for this guy is, I know all three of these are equal for any given frequency. All three of these, or all four of these things are equal to each other. All right. And for me, I just go straight to, for n equal 1, I have the shifted cosine. So I have 4 cosine, I'm going to say theta. Okay. 4 cosine theta, where theta is equal to omega naught t plus 60 degrees. All right. What was omega naught? 2 pi 60. Okay. So when I look at that, I can go to Euler's identity. And I can say, what's Euler's identity telling me? It tells me that if I have an amplitude times cosine theta, I have 4 over 2 e to the j theta plus what? 4 over 2 e to the minus j theta. Right? And if I carry all that through basically in the same way that I did here, I'm going to end up with 4 over 2 e to the j 60 degrees times e to the j omega naught t plus 4 over 2 e to the negative j 60 degrees times e to the negative j omega naught t. All right, 2 vectors that rotate in the complex plane, one forward, one backward, at the same frequency. Okay, so at this point, I have alpha 1 and alpha minus 1. Okay. Somebody other than Jeff, what's alpha 1 and what's alpha minus 1? So first of all, which one of, there's 2 terms here, right? Which term is the n equal 1 and so this is n equals something and this is n equals something here. Which term is the n equal 1 and which one is the n equal negative 1? This is n equal 1. This is n equal minus 1. So this guy is alpha 1, right? If you compare this, what's inside this summation, to what's in those 2 terms, you'll see that I have an alpha, a complex number, times e to the j n omega naught t. The alphas are complex. So when I write 4 over 2 e to the j something, that's one number, right? It has a magnitude and an angle. Okay. It's a complex coefficient, this alpha. Okay. So this guy is alpha minus 1. Okay. So at this point, I know alpha 0, I know alpha 1, and I know alpha minus 1. For this x of t, what other alphas do I need to figure out? Alpha 3 and alpha negative 3. All the other alphas are 0 because there's nothing else in this signal. All right, all the other alphas are 0. So in this case, I've got this character to worry about now. All right, so that guy is in what form of the series here? On the what? So of the Fourier series, what form is 6 sine 2 pi 180 t? Is the what? Yeah, it's the A cosine B sine, right? So this guy looks like I have I think of it this way, A3 cosine 3 omega naught t plus B3 sine 3 omega naught t is equal to 6 sine 3 omega naught t. right? Because omega naught, we said, was 2 pi 60. All right. You guys with me there? All right. So looking at that, I got some stuff to solve for, right? Do I have a cosine term on both sides of that equal sign? No. So what's A3 have to be equal to? 0, because I don't have a cosine. All right. I do have a B3, right? What's my B3 value? B3 value is 6. All right. Now, for me, what I then do is I go back and look at this and say, all right, I want to get this guy into this form. All right. I don't see a direct way to get to the alphas from A's and B's, but I do see a way to get from A's and B's to this form, right? I see how I can get from A's and B's to that form and then to that form. So I'm going to leapfrog. I'm going to go from one to the other, right? So, all right, the formula we had for that was we basically said C3 is A3 squared plus B3 squared. And phi n, or phi 3 in this case, would be A3, the angle of A3 minus JB3, whatever that vector is. Okay, so what's that magnitude going to be? That looks intimidating, but yeah, it's just going to be 6, right? Because I got 0 squared plus 6 squared, square rooted, it's going to be 6. Now, phi 3 is the angle of, let's plug in there, A3 is 0. So B3 is 6. So I got the angle of J6. What's the angle of negative J6? This is where I've had a number of people come to me and say that so arctan, I put that into, so I got arctan of negative 6 over 0. And my calculator says undef. Well, that's because your calculator's brain's too small. Yours is bigger, right? What's the angle of negative 6? What's the angle of negative 6? You said negative 90? So when you're not sure, one thing to always do, if you're gonna use the arctan function, is draw it out for yourself in a complex plane. Here's the real, here's the imaginary. Those are our axes. Where's negative 6 sit? Straight down, negative 90 or positive 270. I could say it either way, right? So this guy is negative 90. I don't need to go to a calculator for that, right? That guy is negative 90. Okay, so that tells me that C3 is what? 6. Phi 3 is negative 90, meaning that 6 sine 2 pi 180t is 6 cosine 2 pi 180t. In fact, I don't want to call it 2 pi 180. I'm going to call it 3 omega naught t minus 90 degrees. All right. Again, if I can go to these formulas to figure out, okay, well, now that I know the C values and the phi values, I can get to the angle, I can get to the alpha value pretty easily. For me, I look at this and I just say, all right, well, I know that I have 6 cosine theta, where theta is now equal to 3 omega naught t minus 90 degrees. And so that's 6 over 2 e to the j theta plus 6 over 2 e to the minus j theta. I just use Euler's identity to write that out. And that gets me to 6 over 2 e to the negative j 90 degrees times e to the j 3 omega naught t plus 6 over 2 e to the j 90 degrees e to the negative 3 omega naught t. Like that. Okay. Yeah.
Don't we just like set 6 cosine e omega naught t minus 90? Since we know that the sine is cosine minus 90, we have to go through all of that? Or like, would it
There's a trig identity that will tell you that.
like, would it always work if you said that, or I have to go through all these steps to transfer it then? There's C cosine.
So I don't like anything that just is for me, right? So there's a trig. So you could say, yeah, sine of x is equal to cosine of x minus 90 degrees. There's a trig identity that states that, yeah, right? If you said, okay, the trig identity that states that, yeah, sure, I'll take it. Right. But I don't think it's a good idea for you to skip those steps because you're not good enough yet. And that's not just you, that's the general you, right? If you're here to gain skills, right? So it's time to, jump through the hoops and, do the obstacle course, right? It's time to train. Right. That's basically, so I think it's useful to go through that process to build up the skills. Okay. All right. So all that said, what did I just do? Well, I figured out here which one of these is the n equal 3 and which one is the n equal -3. First one's n equal 3, second one's n equal -3. So that means this guy here is alpha 3 and this guy here is alpha -3. Right? So now I got all my stuff. I've figured out, back on my first slide, I figured out alpha 0. I figured out alpha 1 and alpha -1. Now I've figured out alpha 3 and alpha -3. So now I want to start mapping those alpha n's to the right frequencies, right? So what do I know here? I have, let's write it out. So I have n, and I want to relate those to frequencies. All right, so what do I have? If I were putting this into MATLAB, like the way that I ask you guys to, right? Where would I start and where would I end my n values in this case? Yeah, -3, -2, -1, 0, 1, 2, 3. Okay. And what frequencies are those going to be? I'm going to say -3 omega naught, -2 omega naught, -omega naught, 0 omega naught, 2 omega naught, and 3 omega naught. I think, yeah. Somehow that stuff always comes up when I do that. All right, this would be 3 omega naught. There. All right. So what do I need to do here? I need to figure out what are the alpha n values. All right, what are the alpha n values here? So first of all, some of these alpha n values are 0, are they not? What are they? 2 and -2. Yeah, those are definitely 0. All right, those are definitely 0. Now we said, let's just go back through. Alpha -3 was 6/2 e to the j90. So let me say I got 6/2. So let's call that 3 angle 90 degrees. Okay. For n equal -1, that is this guy here. So that looks like it's 2 with an angle of -60, right? So I'm going to say 2 angle -60. What did I have at DC at omega equals 0? Without even going back to it, 5. Yep, I can just see it from this, right? It's that. At omega, so without going back to the slides to look at it, just based on what I have right here, 3 angle 90 for -3 and 2 angle -60 for -1. Tell me what the omega naught value is going to be. Well, the conjugate, yeah. What do you mean? So in that case, the angle is going to be the opposite, right? But the magnitude stays the same. 2 angle 60. And what do I have for the third harmonic? 3 angle 90, -90, sorry. Okay. So, all right, that tells me, if I kind of wrote it out pretty explicitly there, but, if I wanted to, I could say, well, there's a magnitude of alpha and an angle of alpha n, right? And you can see what they are there, right? So if I talk about the angle and the magnitude, it's 3, it's 0, it's 2, it's 5, it's 2, it's 0, it's 3. And my angles are 90. What is it? Negative 60, 0. What is it? 60, and then negative 90. I left the other ones blank because kind of it doesn't matter, right? I'll say 0. You notice I don't usually ask for you to give me your 5 because it's a little bit weird because if the magnitude's 0, I could have 0 with an angle of 270 degrees. It's still 0, right? But it makes sense for it to probably be 0. All right. Now so I've got the alpha values. The last step for me is to basically say I need to get x of omega as this set of impulses. All right, so from n equal negative infinity to infinity, alpha n, delta of omega minus n omega naught. All right, so given what I just wrote out here, where do I have impulses? Where does this summation, so from n equal negative infinity to infinity, there's a lot of n there, right? But for most of the values of n, what's true about the alpha n? What's true about the alpha n for almost every n value between negative infinity and positive infinity? What's true about the alpha n values? Well, for most of them, they are equal to 0, right? For most of the n values, alpha n is 0. The only ones we were concerned with were basically negative 3, negative 1, 0, 1, and 3. All right, so I'm going to say, where are there going to be impulses? Negative 3. Okay, so basically n equals 0, plus minus 1, and plus minus 3. Okay, so I'm going to say there's an impulse at, how do I do the impulse at, let's do the easy one, alpha 0. How do I do the impulse at omega equal to 0? How do I express an impulse that's going to be located at omega equal to 0? So when I say omega equal to 0, I mean I'm going to draw an axis like this, right? So omega equals 0. How do I express that? How would I write that delta function? What would be the argument of that delta function? Omega. That would be an impulse located at omega equal to 0. All right, now how do I get one at alpha 1? So at the fundamental frequency, so n equal 1. How do I get that? Gonna be delta of what? Omega minus omega naught, because it's shifted to a positive value, right? So it's shifted to the, what direction would that be? Shift the impulse to the, yeah, from my direction, it's the right? So alpha 3 omega, and how would I write that? Omega minus what? 3 omega naught, keeping you awake. All right. And then what do I have for this guy? I got to do the n equal minus 1 and the n equal minus 3. What do I do for that? Yep, omega plus omega naught. And this guy would be alpha negative 3 omega plus 3 omega naught. Yep. Right? Yep. And so then what I got to do is just plug in the values of alpha. Now, what was the problem with that? Well, the alpha values are complex, right? So how many graphs do I need to make? 2, right? 1 for the magnitude of x and 1 for the angle. So I got 2 graphs to make. All right, now, do it this way. I want to graph it by hand to know. I got code coming, but I want to. All right, what's it going to be? So my alpha 0 was 5. That would be an impulse here of a height 5. Okay. What would I do for alpha 1? Well, alpha 1 had a magnitude of 2 and an angle of 60. So here at omega naught, I would draw something that has a height of 2, so that should be a little shorter, I guess. So at omega naught on the x-axis, I got something that has a height 2. And for negative omega naught, I'd have something that has a height of 2. Or an area of 2, I should say. That's the area of it. And I would say this guy has 60 degrees. And this guy has negative 60 degrees at the same frequency. Now at 3 omega naught, what's my magnitude at 3 omega naught? Well, 3 omega naught, it's 3 with an angle of negative 90. So over here at 3 omega naught, that'd be over here. There's a magnitude of 3 and an angle of negative 90. And then at negative 3 omega naught, you'd have the same height. Sorry, same height here is 3. And the angle would be 90 degrees. This would be minus 3 omega naught. Minus omega naught. Omega naught and 3 omega. Right? Those are my impulses. So you guys can look at the code more closely, but basically what I did was I kind of loaded up my alpha vectors here and ultimately made my 2 graphs. Now the way I did this is I have the subplot command. Right. Now I didn't do this, so the values here that I have, this is omega naught, which if you plug in 2 pi 60 works out to be 377. That's why it is where it is. All right. And you can see the height's 2. The height here is 3. Right. The height here is 5. Right. Just like I said, it was going to be back here. All right. So the code that I've got here, you can kind of look at how I did that. Basically, I just created this alpha vector. I created an omega vector. Right. And in this case, I did it from -7 to 7. All right, I didn't have to, but that means I went past, and you see I got a bunch of zeros there because I don't have anything past the third harmonic. All right, that's basically what you guys are doing in problems 3 and 4. All right, problem 3, you have one just like this, right, where it's basically, something like this one here, and you're doing it what I call by identification. I'm looking at it, I'm identifying that I have this series. For problem 4, you're taking what you did in problem 2. Problem 2, you got your nice friend, the trapezoid wave, right? Which you guys are loving the calculus on that one, right? So you're taking, if you get the coefficients for that trapezoid wave, you're basically just taking those coefficients and drawing the pulses at those points. All right. That's the process.
It's like